and I will put the lecture up online, or you can access it through Collaborate as well. Okay, so yeah, so this week is chapter 3, okay, which is on springs and dampers. As I mentioned last week, there's going to be a mix of it's sort of more qualitative stuff this week, more description, but there is a little bit of maths in the middle that we'll do some examples of as well. But yeah, it's mainly sort of exposing the different things that are going on inside a suspension system. Next week we talk about different suspension types and parameters, whereas this week is really around springs and dampers and those things that actually do the suspension. So yeah, so I thought I'd just do this presentation, go through it. But like I said, there are some in-class questions for this week as well. I noticed in the notes there was I provided some answers, but they're not the correct answers, so we'll have to go through them together. But like I said, we'll do that as we get to them. Okay. So on let me just go back to there we are. Right. Okay. I wonder if I let me see if I present this. Is it gonna? Let's see what you can see. Okay. Okay. No, you can't see them. Okay. So you can all see the slides. Yes. Okay. So yeah. So we'll start off with a little introduction. Talk about different spring types. Okay. The different ways you can get the spring action into a suspension system. We'll talk about stiffnesses and natural frequencies, okay, which are important in terms of ride and handling. Talk about leveration and spring length, how to work out those things, and then talk about specific types of springs that deal with roll, so anti-roll bars and also heave springs, Z bars. Those types of springs which also impact the suspension. There's a very short introduction to dampers and what they do, and a little bit about active dampers, and then at the end there's a sort of description of what we mean by active suspension, including some examples. And I've got some videos as well that I'm going to show you as well, just YouTube clips to illustrate some of these points as well. So yeah, so we'll just go through. Hopefully YouTube will come across okay on Collaborate. Okay, so what's the suspension system? The main aim of the suspension system and the steering system is to maintain the wheels at the optimum angle to the road surface at all times and under all conditions. Okay, because obviously the amount of grip you get between a vehicle and a road is all through the tyre, and obviously if you can maximise the grip between the tyre and the road, then obviously you're going to get safe and good handling. Okay, so obviously that's the main point of the suspension system. Clearly, if you didn't have the suspension system, the car would you can't really optimize for those things. Well, when I say the steering system, I'm meaning sort of all the geometry around the front end of a vehicle with the steering, and obviously we'll talk about some of that geometry next week in terms when we talk about parameters, because there's all the sort of kingpin geometry and steer axis and stuff. But yeah, we'll talk this week about the suspension. And that's the main point of the suspension, is to maintain that contact. Okay, so obviously the other purposes. Isolate the body from road-induced vibration. Obviously, to make the vehicle comfortable, you want to make sure that the suspension can deal with some of the vibration that's coming up from the road. Obviously, as I mentioned, maintain contact between the tyre and the road is very important. Okay, it helps control the body. Obviously, the suspension, because you've got this compliance between the road and the body, that body needs to be controlled in some way. Okay, and the suspension will help do that. You can also limit the wheel movement in the suspension system, obviously the tyre loads, and also it needs to be able to support a range of loads. If you imagine the suspension in a commercial vehicle, a heavy goods vehicle, obviously that heavy goods vehicle may be fully laden or may be empty, and obviously you need to be able to support both of those situations. Okay, so obviously suspension needs to be able to deal with those sorts of things. So there's a depending on what sort of car you're talking about, there's obviously primary and secondary functions. And in a road car, in a conventional road car, the primary function of the spring and damper system is around ride comfort, okay, to occupants over rough road. So yeah, and almost even sort of track focused road cars, it's still around ride comfort in reality, because of the whole idea of driving on the road means you really can't, that needs to be there. Otherwise, people wouldn't drive the car on the road. Okay. Whereas with a race car, the primary function is around optimizing the contact between the tire and the road to maximize grip. Because obviously, in the racing car, it's around lap times, and obviously to go around corners faster, you need to maximize the grip, and that's why racing cars have a slightly different primary function. Okay. So even like I said, even road cars that are track focused, you'll still have there's still going to be an element of ride comfort incorporated into that suspension system. Whereas with racing cars, it's much more around providing good grip, and generally that means stiffer. Okay, so racing cars are invariably more stiffly sprung than road cars, and there are some reasons for that. Okay, so obviously racing cars tend to have a lower ground clearance, less ability to tolerate suspension movement before bottoming out. Okay, so you tend to have a slightly lower ground clearance. That obviously has impact towards aerodynamics. Okay, and if your vehicle on the racetrack does produce downforce, or you've got aerodynamic devices, then obviously that's going to push down on the vehicle and that makes the car run lower as well. So you need springs to oppose that motion to maintain a bit of ground clearance. And so obviously to oppose that motion, you need to have stiffer springs. And those aerodynamic devices that you do have on the vehicle they work best if you've got a stable platform. If you know the ride height of your vehicle, and you know when it's running, when you're at a speed where aerodynamic devices are in play, obviously it's good to know what your ground clearance and those sorts of things will be. Certainly, if you're dealing with vehicles with ground effect, that's extremely important aspect. And this is way before your time, but back in the early 90s, Williams Formula One team, they were at the top of the tables at that time, and they had they actually introduced some active suspension in 92 and 93, and consequently winning everything. But the active suspension, the main purpose of that was to actually maintain a fixed ride height. So they actually knew at all points where how the vehicle obviously it stopped rolling and those sorts of things. But like I said, they also knew exactly where the car was going to be at all times, and so they could optimize their under vehicle aerodynamics to optimize that. Okay, and obviously going around corners, higher G forces during acceleration, cornering and braking causes large load transfers between wheels. I will talk about load transfer when we get to chapter 5, but obviously that's one of the other reasons why racing cars are more stiffly sprung, because you've got to support those acceleration forces both laterally and longitudinally. And obviously, if you've got soft suspension, you get a lot of pitch and squat, you get a lot of roll. Obviously, racing cars that's not so good, so you spring them stiffly. However, there is a compromise, and that is the fact that mechanical grip, so the grip you get between the tyre and the road, you should make the suspension as soft as possible. Okay, and that is so often in performance cars and in racing cars, what you'll have is quite a stiff front end, which is the non-driven axle, but the back axle is actually relatively softly sprung, and that's because of this, the back axle being the drive axle. Okay, but why is that? Why is that the case? Well, let's think about a vehicle, and it's going over a depression, okay, in the road. So there's not so much a pothole, but a depression in the road, and you've got this situation with stiff springs and with loose springs. Okay, and so here we've got two different spring stiffnesses. Soft, we've got 20 newtons per millimeter, and a hard spring of 200 newtons per millimeter. Okay, and so for deflection with the hard spring, a deflection of 5 millimeters, you'll see that the load that incorporates is 1,000 newtons. Okay, if you deflect it by 5 millimeters. Obviously, with the soft spring, you've got much less. You've got 100 newtons of load is required to deflect it by 5 millimeters. Okay, so that's the difference. Okay, so soft spring, so yeah, 50 millimeters to get 100. Yeah, so like I said, you can compare the two springs. These are just spring rates load versus deflection. This is your F equals kx graph essentially. Okay, so like I said, if you pass over depression of depth of 10 millimeters, okay, for the soft spring, what happens is you basically the 10 millimeters as that drops the deflection down, but you've still got 800 newtons of load going through the tyre. So the tyre is still being pressed into the road, but because you've got a soft spring, you're still generating 800 newtons of load. Okay. Whereas with the hard spring, if you go over a depression of 10 millimeters, notice that because the hard spring, you take the load, you reduce this down, you've actually generating negative load onto the wheel. Okay, so basically the wheel is going to go over the depression without being pushed into the road. Okay, so for the soft spring, you've got a 10 millimeter depression. Okay, so that reduces the deflection by 10 millimeters, but you've still got 800 newtons of load going through the wheel. For the hard spring, you go over a depression of 10 millimeters. You've actually gone negative in terms of the load. Okay, and so yeah, so that's basically what's happening in terms, and obviously this load, divide that by the unsprung mass, you'll get a acceleration force into the ground. Okay, and with the hard spring, it runs out of travel at 5 millimeters, and so the best the wheel will only go into the depression through either gravity or it skips over the depression, depending on obviously how big the depression is. Okay. And so so that's why you want a soft suspension with the traction, because obviously any imperfection in the road, you're still providing a lot of input into the road to unlock the grip. Okay, so like I said, so often with racing cars, you'll see front suspension being quite hard. There'll often be an anti-roll bar with the front suspension, but at the back you want it quite relatively soft, and you tend to have slightly looser in terms of the roll stiffness as well. So some cars will have a front anti-roll bar, but not a back anti-roll bar, and those sorts of things. Okay, so that's the importance of having a relatively supple rear end on your car. And another, an anecdote about that, back when the R35 GTR came out, Nissan GTR that came out a number of years ago now. There was one of the things about it was double clutch gearbox and launch control. And this mighty vehicle could launch extremely far and extremely well. But to get it into launch control, there were various settings you had to put it in R mode for the gearbox and then the throttle, and there was also an R mode for the suspension. But to actually get it into launch control, you had to make the suspension soft, and that's the whole idea behind that being to get that better traction. Okay, so yeah. Okay, so that's stiffnesses. Okay, so we'll talk a bit more about stiffnesses when we get to the end of this section. But this is about different spring types. Okay, so this is going back to that thing. So for the soft spring, the spring force drops to 800 newtons. So an average of 900, because obviously it's 1,000 and 800 the average. So the acceleration of the wheel downwards into the road was you take your 900 newtons force divided by the mass of the unsprung mass of the wheel. So you've got 3.7 G pushing the wheel down into the road. And obviously for the hard spring, the spring force drops to 0. So you've got no acceleration. So the wheel drops either due to gravity or hovers mid-air until the road comes back up to meet the tyre. So different spring types. The first most obvious type I'll talk about is a coil spring. Okay, there's some pictures there of a coil. These are that item inside the coil. On both these is probably the damper. Okay, so often they're combined into a single unit, and clearly a coil spring. How a coil spring works, it's a helical coil. and as you obviously as you deflect the coil or the length of the spring, you get a spring force in the other way. Okay. The most common implementation, most cars generally have coil springs. But a few cars have slightly different setups, but I'll talk about those in a minute. But yeah, coil springs is by far the most common. And big advantages of that is around packaging. They're quite small for what they can do, and it gives you lots of freedom in terms of how you configure your suspension system. Because they're the most common, they're low cost, okay, relatively straightforward to manufacture, and because of the fact they're on every car means that you've got economies of scale there, so they don't cost that much in the grand scheme of things. But what they can't do is they can't locate an axle or a wheel. Okay, there's no, if you look at the spring, you've got the spring is very much around the deflection, of the spring up and down in one direction. So that means that you can't use the spring to actually locate an axle or a wheel. Okay, it doesn't provide any support in the sort of off-axis way. Okay, so you need some linkages in addition to the spring to support that. Okay, and another advantage, obviously, friction is a damaging thing for all suspension systems. You want to try and minimise any sorts of friction because you want to do the damping of the suspension system. You want that to be the main focus of the damper unit or the split shock absorber. You don't want any sort of unintended friction. And so that's obviously that's big advantages and disadvantages of coil springs. Okay, so again, there's a more defined list here, advantages and disadvantages. So like I said, easy configuration packaging, low cost, no internal friction. They don't take up much space, maintenance free, obviously unless it breaks, in which case you obviously need to replace it, and you can get large deflections. But like I said, you need some additional linkages for suspension location, and the spring characteristic generally is not variable on the fly in a sense. You can get non-progressive springs, so F equals KX is a straight line, but depending on, you can design the spring such that it gives you rising rates. There's some examples in the notes. I haven't got the picture here of different coil springs and how you can change the parameters of the spring to get rising rates and stuff. So like I said, obviously you can often stick the shock absorber inside the spring, so that obviously helps in terms of arrangement. Like I said, you can get progressive springs. Okay, geometry of the springs can be changed to give you that progressive rate. And these, I guess, characteristic curves are generally linear. Okay, unless you've got a progressive spring, and the natural frequency drops with increasing load. So the more load you put into onto that spring will cause the natural frequency to go up. To go down. And if you think about natural frequency being the square root of stiffness over mass, okay, if your load goes up, your mass goes up, which means the natural frequency drops. So obviously that's one thing to bear that in mind. So if you're working out K of a spring, then you can do that from some basic parameters. So you've got the diameter of the wire, or the actual what the coil diameter is. Then you've got the coil diameter, so that's the outside diameter of the whole spring. Shear modulus G, which is a property of the material, and then you've got the number of coils N, and the rate that's given in Newton meters can be calculated. Okay. So with the progressive spring, there's the pictures on page 26 in your notes. You can see you can have a different core diameters. Okay, you can have different wire diameters, which is picture B, and then C you've got a core spacing. So you've got coils that are widely spaced apart and then close, and then obviously D is a mix of all those things. So you've got different coil diameters, wire diameters, and spacing. Okay, you can get those and they will give you a non-straight line value for K, depends on depends on the deflection, what value of K you've got. So they give you progressive rates. Okay, the next spring type we'll talk about is called the leaf spring. Okay, this is possibly slightly older-fashioned. You can find them on horse-drawn carriages. The sort of basic implementers of leaf springs, and the main it's very straightforward to sort of understand what goes on. You've got basically a leaf of metal, and obviously as you deflect the wheel, that metal will bend, giving you some suspension. Okay. They can be used to locate an axle. Obviously, that's one of the advantages. But often you still have additional linkages. Yeah, so that's the leaf spring. Okay, the old type of spring can be used as a linkage. Okay, often there'll be more than one layer, multi-layer leaf springs. But obviously, one of the issues with that is those leaves will rub against each other, which can lead to some negatives. So you've got some internal friction in a sense there. Okay, and that may that can lead to negative responses and acoustic influences. So obviously you need to lubricate between the leaves. You've got quite limited deflection. Okay, but like I said, because they're of their cheap and simple construction, you're more likely to find them in commercial vehicles. If you look at some light small goods vehicles, vans, and those sorts of things, with either a solid rear axle or just a simple linkage between the two, you'll often find leaf springs. So the back of I don't know, like a Ford Transit or something, a front-wheel drive Ford Transit, you'll see the leaf springs there. Oh yeah, and like look at the back of lots of older cars as well, and you might see leaf springs as well. But they are still used in some modern cars in interesting ways. So, for example, the Corvette and interestingly the Volvo XC90 has a transverse leaf spring. Okay, so one of the obviously advantages here is the intrusion into the passenger body of the car is very small because you've got this green item here, which is a leaf spring. So in the XC90, that's actually a composite. Okay, it's made out of some sort of composite material, and you can see that it's very simply you've got the linkages at the top and the bottom there, so sort of wishbones, and obviously as the wheel deflects, it bends the leaf spring, and you've got this one leaf spring dealing with both sides of the suspension. Okay, and that's clamped to the body, the chassis here. So, like I said, that's quite a nice sort of neat setup, and I know certainly up until the C7, we call that 7th generation, they certainly had a leaf spring. I'm not sure whether the new mid-engine one has a leaf spring still, but like I said, certainly up until C7 they had that sort of setup. And like I said, you can see there's big advantages of using this setup in terms of the intrusion into the passenger's body. So yeah, good transfer of forces to the chassis, can be used to locate the axle, and it's very low cost. But as I said, often with metal leaf springs, and certainly with multi-layer, you need to maintain them. Friction between the layers can obviously be a problem. That can also cause a noise, so that's not great. Okay, they can be heavier than coil springs. Okay, if you've got a solid axle implementation, then obviously that's quite a lot heavier. And if you want to avoid axle tramp, which is deflection due to drive forces, then obviously you need some additional linkages to help locate the axle backwards and forwards as well as side to side. Okay. The assumption of the suspension linkage functions. So, like I said, you can assume the linkage is part of that leaf. Okay. The leaf is generally quite wide, which gives you some lateral support. Okay. Like coil spring, the natural frequency will drop with increasing load. Okay, and the characteristic curves are generally linear. Okay, but yeah, but like I said, it's quite an old-fashioned type of leaf spring, although it's used in that arrangement there. And again, like the coil spring, you can just use an equation to work out the stiffness. It's a simply supported flexible beam, so this is basic sort of statics. You've probably seen this equation like this in stress and dynamics in the first year, but E is Young's modulus, B is the leaf width, T is the leaf thickness, and then you've got the length of the leaf there, and so you've got your BT's cubed term there over the length, and that will give you the stiffness of the leaf. Okay. Next type of spring is called a torsion spring. Okay, torsion indicates that you've got something that is subjected to torsion, so that's a twisting. Okay, so and so what you'll often have is connected to one of the suspension arms. So if you've got a double wishbone or a strut based suspension system, then there'll be an arm. Okay, and that will be connected solidly to one end of the torsion spring, and the other end of the torsion spring will be connected to the chassis. And so as the suspension moves, that suspension spring, the torsion spring, will be twisted, and that obviously provides your thawing energy, which can then be exerted on the force. So again, you've got a stiffness there. So that's operated by one of the suspension arms. Often, in terms of material science, the way they're manufactured, you shot peen and scrag it to increase fatigue life, because obviously the constant twisting is going to cause fatigue. Essentially, a coil spring is also twisting as it's compressed as well, but generally, so that came up on this. Like a coil spring, they're wear-free and maintenance-free. Obviously, if it breaks, you will replace them. Okay. And interestingly, one of the things with the torsion spring is very straightforward to make ride height adjustments. You just need to alter the clamping point of the torsion spring, and so you can make that quite easily sort out the ride height. Okay, but obviously one of the disadvantages is the fact that the space constraints, they're not actually that big themselves, but depending on how you've implemented it, you need quite a long space to require stiffness. Clearly, there are various things that will affect the torsion springing characteristic, and that's obviously things like diameter and whether it's a solid tube or a hollow tube and those sorts of things. So there's a sort of schematic. So you've got your suspension arm here, we've got a double wishbone suspension here. And you can see that the suspension mounting point, very close to that, you've got this clamp onto this torsion bar. And then, like I said, it will also be clamped to the chassis. So as this suspension deflects up and down, you get a twist of the spring there. I heard a ding. So a question. Well, the anti-roll bar is actually a torsion bar. Okay, but I'll talk about anti-roll bars in a minute. But yeah, they are different. Yes, you can have torsion bars as the primary suspension unit that controls the deflection up and down. But yeah, anti-roll bars are often a torsion bar as well. But I'll talk about I'll talk about that in a minute. But yeah, but you can, like I said, you can find torsion bars being the suspension unit too. I think a lot of certainly in the past, many former student cars have used a torsion spring as their spring stiffness. Like I said, it's being just a simple piece of metal, it's actually relatively cheap. Okay, so wear-free and maintenance-free, depending on the design, ride height, you can adjust the ride height. I guess the other advantage in there is the fact that the cost is relatively cheap. Obviously, they've got to be quite long generally to give you the required stiffness. And the wheel-related spring rigidity depends on the suspension arm arrangement. Obviously, how the suspension is designed will give you those different characteristics. Made of round steel for low weight or flat steel with increased stress. Okay. Again, natural frequency drops with increasing load. Okay, so you put the load up, the frequency will go down. And the characteristic curves are generally linear. Okay, and again, by using some simple maths, you can a standard equation, you can work out your stiffness, and that will obviously give you the stiffness in terms of a torque per degree as opposed to newtons per meter. So Newton meters per radian or Newton meters per degree. Okay. Right, so those are the sort of standard springs. Then we can move on to gas springs. Okay, so there's two types of gas springs that I'll talk about. There's the simple sort of air spring, a bellow, and the hydrogen pneumatic, which is a mix of two different mediums. Okay, and the spring force will change due to the volume of a gaseous medium. Okay, so the bellow air spring is obviously clearly you can quite easily adjust the ride height by just supplying additional air. You pump more air into it, you increase the ride height. And one of the advantages of air springs is you get a constant natural frequency with the rising load. Okay, so the load will have no impact on the natural frequency. And one of the main uses of air springs is actually in luxury cars, and that's the advantage of luxury cars. Like I said, the suspension could be finely tuned to give you a good ride, irrespective of what the load is in the vehicle. And you often find the back end of lots of estate cars, high-end estate cars, so like the 5 Series and the E-Class and those sorts of things will have air springs, certainly at the rear, again about the ride comfort, but also because there'll be a standard ride height, irrespective of the load, because you can, like I said, you can pump them up a bit more. Hydrogen pneumatic, basically that gives you a mixed medium, so you've got hydraulic fluid and also an air bellow. Okay, when I say mixed medium, they're not going to be in a homogeneous mix. You'll have hydraulic fluid and an air bellow, being separated by a membrane. Okay. Again, you can control the ride height, but this time instead of applying additional air, you supply additional hydraulic fluid. So you can obviously increase the amount of hydraulic fluid, which will give you ride height. And the interesting thing with this setup is that the natural frequency will go up with increasing load. Okay, it's just due to the way that the suspension is designed. So here's a couple of this is a so that on the left we've got the hydro pneumatic setup. Okay, so obviously here you've got an accumulator type thing, N2 being nitrogen. Obviously there's your gaseous content, and then below the membrane there's a rubber membrane inside the accumulator will be hydraulic fluid, and that's connected up here to your hydraulic supply. And one of the big advantages of this setup is that by like I said, you can adjust the ride height by applying more and less hydraulic fluid. The other big advantage is the fact that the damping, the flow through this orifice, can be incorporated into the spring. Okay, so often you don't need a separate damper. You've got the damping incorporated because obviously dampers generally flow through an orifice. If your spring is actually flow through an orifice, then you can combine the damper into the spring unit as well. So you've got this setup. And again, before your time, but in the past, many Citroens used to have this sort of setup. And if you look at classic Citroens like the SM and the DS, they've all got this sort of setup. And they were using them well into the 90s with the vehicles like the Citroen BX and the XM, and even the Xantia. But like I said, I think this is all way before year 2000, so before your time probably. So like I said, so that's a hydrogen pneumatic setup. This is a simple air bellow. It's just like a balloon basically. You've got air inside a rubber sort of membrane, and like I said, that's and you've got obviously it's got like a balloon. They've got to be quite a lot more robust, but basically it is like a balloon. So with air bellows, comfort is, as I mentioned, is irrespective of or independent of payload, and obviously you've got the ride height adjustment there. They don't apply any support in other directions. So again, like a coil spring, you need additional linkages. And if you've got low pressure inside that air bellow, you need quite a big volume to give you the adequate requirements. Information is soft vertical spring rigidity. Okay, air spring, strut or individual spring can be found in commercial vehicles and buses as well. So if you look at the back end of a big dumper truck or articulated trailer, you'll often find air springs there as well. again to do with the ride height stuff and deployment in passenger cars for ride comfort. Like I said, they're very comfortable, and you obviously control the ride height, as I mentioned, of the rear axle, or all-round suspension. And the natural frequency remains constant with increasing load. So, like I said, that's quite a good thing if you're trying to tune your natural frequency of the suspension to give you good ride. But obviously, it doesn't matter how heavy the load is, you'll get a constant natural frequency. And like I said, it depends on the gas being used for the characteristic curve. For the hydrogen pneumatic, you get damping inside. Like I said, damping comes included, and the ride height control is easy to do. There often might be a maintenance requirement. Like I said, one of the things that will eventually wear out are these bellows, or this accumulator, and so you'll have to replace that. But it's generally straightforward. You just screw a new accumulator on. The volume in the spring and the accumulator determines the characteristics, because essentially the hydraulic fluid is, in a sense, pretty much incompressible. So obviously this is the gas in here is the thing that provides the spring, like an air bellow. Obviously the hydraulic fluid in there gives you will allow you the damping. Okay, integration damper valves in the shock absorber. So it's part of the same unit, and then the natural frequency rises with increasing load, which is non-linear spring rigidity. Okay. So those are the main spring types. At the end of the travel of the spring, you'll have a bump stop. Okay, and that mainly is there to prevent the spring or the suspension bottoming out and ending up with metal on metal contact. Okay, which is very, very undesirable. Okay, and so the bump stop will provide an additional bit of compliance, but will basically gradually, once the springs run out of travel, it will then start to deform. Okay, and so you've got a much higher stiffness of the spring, but obviously it will still be compliant, so giving you this transition from the spring rate to the final stopping point. Okay, so like I said, much higher stiffness than the suspension spring. So often these are rubber units connected to the end of a suspension unit, and like I said, it depends on how the suspension is designed, but it could be a simple just rubber stopper like this sort of thing, or you can have some quite complex shapes. So, for example, here you've got this rubber thing. Clearly, this bit is going to deflect first, and this bit, and then even that whole unit is then contained within a rubber sort of bush type thing. So obviously, as this comes to the end of its travel, it slowly changes from one stiffness to before it actually stops, bottoms out. Here you've got a simple sort of like a rubber spring type thing. As this comes up, that will compress this rubber unit. And again, this is very similar to this. And you can see this is probably connected to a leaf spring. So you often find with leaf spring vehicles, in addition to the spring, there'll be some sort of rubber bump stop that will stop when the leaf sort of gets close to hitting the chassis. There'll be a bump stop to stop that from happening. So you get these sort of rubber things like that. Okay. Right, so this is where we get into a little bit of math and analytical things. Are there any questions on the spring stuff? Like I said, quite descriptive, and all the stuff is in the notes. Okay, so if there are no questions, let's move on to this stuff. Okay, so this picture here is a car model. So for those of you remember from operational dynamics, this is something that we looked at briefly. And so you've got the sprung mass, MS, okay, and the unsprung mass, MU. So sprung mass would be the vehicle body, unsprung mass would be the wheel, the hub, often the brakes, and basically half the suspension linkages, because they connect the two. And then obviously they can deflect independently of each other. So you've got the ZS, the ZU, and then obviously the ground can also be a deflection too. And then between those various masses, you've got the springs. You've got between the sprung mass and the unsprung mass, you've got the suspension spring, KS, and there'll be a damper as well, CS, in there. And then obviously between the unsprung mass and the ground, you've got a tyre, which will also have stiffness, KT. The damping between the tyre and the road is minimal, so it's often neglected. Okay. And so with this car model, there's a couple of ways the vehicle the system can vibrate. Okay, you've got 2 degrees of freedom, so there's going to be 2 modes of vibration, and those modes for this application has 2. They've got specific names. Okay, so there's basically mode 1 is known as body bounce, and what you do with that is you neglect the mass of the unsprung mass here. Okay, and in which case you then end up with springs in series. Okay, so basically this mass is going to be a lot smaller than MU's, a lot smaller than MS. So you assume this to be 0, and so you end up with 2 springs in series, which gives you the spring stiffness for the sprung mass. Okay, if springs are in series, the spring rate, okay, the total spring rate is going to be the inverse of that will be the inverse addition of those 2. So you're doing a bit of algebra and manipulating, you get KSKT plus over KS plus KT. Okay, so there's your spring rate, and obviously you divide that by the sprung mass, square root it, divide it by 2 pi, it gives you a frequency in hertz of the body bounce of the body chassis. Okay, so there's that equation there for the natural frequency. The second mode is known as wheel hop, because basically what you do with that is you assume that MS being so big is essentially stationary. Okay, and so now you've got MU, but you've got power springs in parallel. KS and KT are both controlling the position of MU between those 2 sort of solid objects. Okay, and that's called wheel hop. Springs in parallel, so you just add the spring stiffness to get the total stiffness, and then you divide that by the unsprung mass, and that will give you the wheel hop, or the unsprung wheel motion. Okay, relative to the chassis frequency. Okay, so that's your FU. So you've got FS and FU. Okay, and then that leads on to this in-class question. So 2 normally similar. That should be similar racing cars. Each have a corner sprung mass of 90 kilograms and an unsprung mass of 15 kilograms. The tyre vertical stiffness is 220 newtons per millimeter. The one car is soft with a spring stiffness of 15 newtons per millimeter, and the other is hard with a sprung stiffness of 150 newtons per millimeter. For each of them, work out the sprung and unsprung natural frequencies for each car. Okay, so that's we can have a go at this question. If I change what I'm sharing, let's have a quick look. Okay, so if I go back to collaborate, I'm going to stop showing this and I'm going to share something else. Share this window. Can we all see that? So these are the notes. This is the page 34, where you've got the question. Okay. Yeah, and so we're going to go through and work out. So we've got different. We've got MS being given to us. If I go for blue, so MS is 90 kilograms. MU is 15 kilograms. We've got KT being given to us. That's 220. Oops. So I'm converting that into newtons per meter, because obviously we need to make sure that we're in SI units. So newtons per millimeter, if you multiply that by 1,000, you'll get the newtons per meter. Okay, and we've got 2 different cars. We've got the soft car. So with that, we've got our KS. So it's 15 times 10 to the 3. Okay, so for the soft car, it says what's the sprung and unsprung mass natural frequencies. So for the body bounce, okay, I'll call that BB. The frequency is 1 over 2 pi. This is in hertz, okay? And we've got basically KR over MS, where KR okay, so we just plug the numbers in, 1 over 2 pi. We've got 220 times 10 to the 3, 15 times 10 to the 3, over MS, so that's 90 kilograms, and that's going to be 235 times 10 to the 3. So let's do the sums. 223, 15, 3, multiply them together, divide by 90, over 235 E3, square root it, divide by 2, pi. 1.98 or 99 hertz. Okay. The wheel hop for the soft car, FOU, okay, is 1 over 2 pi, MU, sorry, oops, KS plus KT divided by MU. Just plugging the numbers down here. So again, 235, 3, 3, 19.92 hertz. So that's for the soft vehicle, okay? For the vehicle with hard suspension, we've got the same equations, BB, body bounce. So the frequency, 1 over 2 pi. So this time we've got 220 times 10 to the 3, 150 times 10 to the 3. And at the bottom we've got 90, so that's going to be 370 times 10 to the 3. Add those two things together. And so 220 E3, 150 E3, multiply those together, divide by 90, divide by 2, oops, 370, square root it, 2 pi, 33 hertz. 33.4 hertz. Not comfortable. Wheel hop. Oops. 220. Twenty-four, 25 hertz. 25, around 25, yeah. 25. Okay. That's wrong. For the FS, I've got that. It's done something obviously skewy for the calculations. That should be the equations, right? The answer's 5 hertz. I was thinking it was a bit high. Okay, so those are the two solutions to that up there. Okay. Interesting, with ride, you want something between, generally, to be comfortable, between 1.5 and 2.3 hertz for body bounce, because this frequency matches your natural gait as you walk along. Your natural gait will be 1.5 to 2.3, so your body is conditioned to find that relatively comfortable. Okay, but if you go above 2.3, so like this value, it starts to be quite uncomfortable, and certain frequencies will induce nausea. Other frequencies, your eyes won't be able to focus on a single point, those sorts of things. It affects the body. And if you go less than 1.5, that can also induce nausea, and that's the frequency at which you get like travel sick, or if you get sick on a boat, seasickness. That's because the boat will be oscillating at a very low frequency, and like I said, if you're not looking at the horizon, or you can't match that, then obviously that's what causes you to become seasick on a boat, because of that frequency. So it's quite important to get the frequency right for ride comfort. And like I said, that 5 hertz is supposed to be okay for a racing car with stiff suspension, but it's not so okay for road cars. And like I said, that's also the advantage of having air springs, because you can tune this to be what you need it to be, and it won't be affected by the mass on the bottom there, because this is for standard coil springs, not for hydropneumatic springs. Okay, right, so that's that exercise. It's a bit difficult to do this as an proper in-class exercise without some over collaborate, but there we go. Have we all got that down? Yep. Okay. Thanks, Karen. Okay, if I stop sharing that and then go back to sharing the PowerPoint or the slides. Okay, so that's natural frequencies. Okay, the next bit is about lever ratio. Okay, so up to now, when we're working out spring stiffness and stuff, we've assumed that the suspension spring is directly attached to the wheel hub. Obviously, in reality, that's not the case. The wheel hub will be located at some point, and the spring will be connected to the suspension linkage at some other point. And so often, suspension there'll be a wheel lever ratio between the two. Okay, and that depends on the packaging and those sorts of things. And so, obviously, to work out the wheel center rate, so the rate of the spring actually at the wheel center, so not the tire and not the wheel on the road, but the between the chassis and the wheel center, which is what we're using for, on the previous example, that was our KS term. That's not necessarily the stiffness of the spring, okay, because there's the lever ratio involved. So, here's a schematic. So you've got the body of the vehicle there at the top, okay. You've got your spring down here, which is K spring, which is the stiffness of the spring, and that's connected to distance RS, ratio of the spring, to the pivot point, which we called A, okay. Now, obviously, the wheel is a distance R from that pivot point, okay, and so obviously you've got a spring force being applied, which is going to give you a deflection of ZS, and the wheel is going to be, if that ZS exists, then obviously there's also going to be a deflection here of the wheel, ZW, and that's going to be the force of the wheel. And obviously that thing needs to balance, unless it rotates around the pivot point. And so you can do some moments around this thing. So you can see that Fs times by is in the positive direction. So Fs divided by Zs will be the rate here, and obviously go the other way here, Fw. So Fs times Rs will be the moment going clockwise. Fw times by R will be the moment going the other way. Okay, so you can actually do those moments. Okay, so yeah, so referring to the free body diagram, we can see that Fs is K spring times by Zs. Okay, where K spring is the stiffness of the suspension spring. Taking moments about the pivot, you've got Fs times by Rs minus Fw times by R. Okay, obviously you replace Fs with this term up the top here. K spring Zs goes in there, minus Fw times by R, that equals 0. And so those two things are equal to each other. Okay, you put the other on the other side, you end up with those two things equal to each other. And so you can solve for Fw, the force in the wheel. Okay, is this Zs times by K spring times by Rs over R. Okay, and then if you go back to the at the wheel rate, so that if we go back to this over here, we can work out the stiffness here is Fw divided by Zw. Okay, so that will give us the stiffness, effective stiffness of the wheel. Okay, and if you stick it, we found the and we know from geometry the Zw, there's a simple ratio between the deflection at this point and this point. Okay, which is simply the ratio of those two distances. Okay, so we know that to be true. So we've replaced Zw down here with this term at the bottom. Okay, replace Fw with this term here. Fw this term here. Put those two things together, and you end up with those two equations, or this equation, simple equation. And if we assume that Rs divided by R, well, obviously, yeah. So Zs they cancel out. We end up with Rs squared over R squared times by the stiffness of the spring. And if we replace Rs over R, so replace R over Rs with the term lambda, that's called the lever ratio. And so if you divide the spring stiffness by your lever ratio, you get the wheel rate, okay, or wheel center rate, Ks. Okay, so that's basically just a bit of theory that goes behind. But this bit is the equation to remember. Okay, that bit there. So if we go back to the here, so like I said, you've got your force at the spring is going to be the stiffness of the spring times by the deflection of the spring. Going through with solving for moments, setting everything equal to 0, you can work out the force of the wheel. If you divide the force of the wheel by the deflection of the wheel, you get the stiffness of the wheel. Okay, and then if you replace Fw with the term with the force of the wheel on the previous slide, and you replace Zw with the simple ratio relating Zw and Zs to each other, and then you stick them together and you solve. Like I said, the ZS's will cancel. You've got this R squared over RS squared term, okay, in this equation, or R squared over R squared term in this equation. Multiply that by the spring stiffness, you'll get the wheel center stiffness. And if you flip them upside down and call that lambda, if you divide the stiffness by the lever ratio squared, you'll get the spring stiffness, the wheel center stiffness. Okay, so that's basically how that works. Remember, in your calculations for frequency, you need this effective spring stiffness for Ks. Okay, not So there's another exercise here. Notice that these values that are shown in your notes are also incorrect. So if I go back to, I just opened the different slides, I think. So, there we go. That's what the slide should look like. So you can see. Yeah, there we go. Right. Okay, so let's have a go at this problem. So a car with a quarter sprung mass of 200 kilograms and an unsprung mass of 23 kilograms has tyres with a stiffness of 180 kilometers per meter and a suspension spring stiffness of 80 kilometers per meter and a lever ratio of 1.6. Determine the wheel spring rate, the ride rate, the body bounce natural frequency, and the wheel hop natural frequency measured in hertz. Okay, so again, I shall stop showing this and share a different window. Okay, so this is on page this is on page 36 in your notes. Okay, and like I said, those terms are those values there are actually not the answers to this. Okay, so I'm going to cross them out. Let's solve this problem. Okay, so we're going to part one, the wheel spring rate. Okay, so we've got these K spring has been given to us as 80 times 10 to the 3 newtons per meter. We know that Ks, the wheel rate, is K spring divided by the lever ratio squared, because the lever ratio is 1.6. Okay, so we've got 80, 3, 6, 50. No, 80, hold on. We need to square that and then divide by. It's only 1.25, that makes more sense. Let's move that all that over. Okay. So 31.25 is the kilonewtons per meter is the answer. So the ride rate, KR, this is where we do the KS KT divided by KS plus KT. So that's going to be 220. No, it's not. 180 times 10 to the 3. We've got 31.25 times 10 to the 3 divided by 180 times 10 to the 3 plus 31.25 times 10 to the 3. Okay, if we do that sum, (26.6) times 10 to the 3. 26.62. 26.62 times 10 to the 3 newtons per meter. So that's your wide rate. So that's the springs in series. Okay. So that's 2, 3, body bounce natural frequency, Fs, 1 over 2 pi, Kr over Ms. So we've got sprung mass of 200. So we take our rate divided by 200. So let's do that. So we take that rate, 200, we divide that there, square root it, we divide by 2 pi. 1.836, 1.84. If you can hear banging and knocking outside from my microphone, I apologise. We're currently having scaffolding put up around our house because we're having the roof replaced next week. So, for part 4, wheel hop, so Fu, 1 over 2 pi, so this will be Ks plus Kt over Mu. So we've got 26.62 times 10 to the 3 plus, no we haven't, Mu is 23 kilograms, isn't it? Yep, 23. So 31.253, add them together, divide by 23, square root, divided by 2 pi, 15.25. So the unsprung mass, or the wheel hop rate, is 15.25 meters per second. Sorry, hertz. What's the question? Yes, you have a break. Let's go for a break. If we come back at what do you want? 10 minutes? Will that be sufficient time? Yeah, okay. So we'll come back at 5 minutes past 1. So set the alarm, and that's when we'll start again. Okay. I shall stop the recording. So we're back at 5 past 1. Okay. Okay, so I should turn off. So yeah, see you in about 10 minutes.